All right, so again, thank you everyone for having me this morning. If I say some strange things, it's because it's 4:30 in the morning for me and I'm still half asleep. So my name is Peter Scarfe. I am the creator of a new framework called Workers for LabVIEW. I have a personal background in mechatronic engineering and computer science. I am a certified LabVIEW architect, and I've been developing in LabVIEW now for approximately 13 years. So what is Workers? So Workers is a queued message handler based framework for LabVIEW. Other queued message handler based frameworks that are popular in the LabVIEW community are DQMH and Deactive Framework. DQMH is what I call a classic LabVIEW based framework, meaning it is not object oriented. It's actually based on the LabVIEW queued message handler template. And then we have the Active Framework, which is a heavily object oriented based framework. And I'm introducing a new framework called Workers. Workers is also an object-oriented based framework, but it allows you to develop in the style of the LabVIEW queued message handler template. And each of these frameworks can be used to develop multi-process applications in LabVIEW using the queued message handler design pattern. In this presentation, I'm going to introduce to you the main features of the Workers framework. I'm going to introduce the framework scripting tools and messaging API, and then show you how to create a small application in a live demonstration. But first, let me start by explaining why I've spent several years developing a new framework for LabVIEW. So approximately 10 years ago, I started a new job as a control systems engineer at a university. And it was my responsibility to create the control and data acquisition systems for several of the experiments at the university. And I decided to use LabVIEW to do this. Up to this point, I was a self-taught LabVIEW developer, so I decided to attend the LabVIEW Core 1, Core 2, and Core 3 courses to make sure that I was going to be moving forward and developing with the best practices. And I was in the Core 3 course where I was introduced to the queued message handler design pattern in the form of the LabVIEW queued message handler template. So I left the Core 3 course feeling that I now had the knowledge to develop the multi-process applications required for the university using the LabVIEW queued message handler template. What I did not know, however, at the time, is that there's no easy way to create a multi-process application out of several LabVIEW queued message handler templates. So I started looking around for examples that were built out of more than one LabVIEW queued message handler template, and I found the LabVIEW continuous measurement and logging sample project that comes with LabVIEW. It consists of 3 queued message handlers, one for the user interface of the application, and one for the acquisition and one for the logging of data. But to create an application like this, you need to manually create and integrate every queued message handler together to build up the frame of an application. I started out myself developing applications this way, but soon realized that it was a very time-consuming process, and I was spending more time creating and debugging the frames of my applications than I was spending time to develop the core functionality of each queued message handler. So the good thing about the LabVIEW queued message handler is that it's easy to use and learn. And it is taught in the Core 3 course as part of the official NI training certification program. But in its current form, it's not modular, it's not scalable, it's not extensible, and no debugger exists that is designed specifically to debug applications built out of several of these. So using this template to develop large multi-process applications is a very time-consuming and inflexible process, and to create the frame of a quality application out of many of these requires much more experience and knowledge than what you will acquire in the Core 3 course alone. Which is why we have the NI training and certification path to train our developers over many years to learn how to properly architect the frames of their applications until they're ready to demonstrate that they can architect the frame of a multi-process application for the CLA exam. It's a long journey, especially from Core 3 to CLA. And when I took the CLA exam myself a few years ago, I realized that the main difference between what you learn in the Core 3 course and what you need to demonstrate in the CLA exam is one of scalability. You need to demonstrate that you can scale a single process into a multi-process application. So up to and including the Core 3 course, you learn the basic LabVIEW concepts and design patterns, And then afterwards, you go out and you work on projects and you learn how to scale and modularize the concepts that you learn in the Core 3 course. So again, the first part here, you learn the fundamentals that you need to be able to develop with LabVIEW. But a lot of what is required in the second part can be replaced with a good framework. Personally, when I came out of the Core 3 course, I was excited. I wanted to develop all these applications with lots of cute message handlers. And I looked for an easy way to scale and modularize what I'd learned in the Core 3 course, but there was no easy way to do this. And for this main reason, I decided to develop a new framework. So the requirements of my framework became the following. It was very important that the cute message handlers in the framework had the same look, the same feel, and the same style as the LabVIEW cute message handler template, so that Core 3 level developers would feel comfortable developing with the framework. The cute message handlers in the framework needed to be modular and allow their content to be encapsulated. Modularity also provides a way for every cute message handler to become like a reusable package. The cute message handlers in the framework need to be easy to scale. This means that a common interface is required by each cute message handler so that you can easily plug them together, much like you can Lego blocks, to quickly build up the frame of a multi-process application. And this can be done by either statically linking cute message handlers together or by dynamically loading a cute message handler from another cute message handler dynamically during runtime. The framework should have a dedicated debugger that can complement the standard LabVIEW debugging tools and add greater accessibility and transparency to your running applications. The framework should use a priority queue for the communication channels between cute message handlers, much like the active framework has, allowing developers to assign priorities to their messages. And the framework should be built with object-oriented LabVIEW, providing the power of inheritance to the framework's architecture. Inheritance means that the framework's common API can exist in a common parent class to all cute message handlers, which minimizes the amount of duplicated code required in each cute message handler. And inheritance also allows you to override VIs and makes it easier to develop hardware abstraction layers using the framework. And finally, I wanted the framework to work on both Windows and NI RT systems, so real-time systems. And currently, the current version of Workers runs on Windows, and the next version of Workers coming out in a few months' time will also run on NI RT systems, such as Compact Rios. So these were the fundamental requirements of the framework. So moving on, what is a worker? So the framework is called Workers because a modular cute message handler in the framework is called a worker. A worker is a cute message handler that is encapsulated in a class, which inherits from worker.lv class, which is the parent class of all workers. Now, for developers that have no object-oriented LabVIEW experience, you can still comfortably develop with the framework. The framework was developed for developers at the Core 3 level without object-oriented LabVIEW experience. These developers only need to understand that a class is much like a library with its own data type. And that's all you really need to know about the use of classes in Workers if you have no object-oriented LabVIEW experience. If you do have object-oriented LabVIEW experience, then you can use the framework and develop with inheritance, and I'll explain the advantages of this later on in the presentation. So what does a worker look like in LabVIEW? Here we have a project containing 4 workers: worker A, worker B, worker C, and worker D. Let's have a look at the contents of one of the workers. Let's select worker D. What you see here are the fundamental parts of a worker. There is a main VI. This is where the worker's cute message handler exists, and an initialization data cluster. And this is used to pass data into the cute message handler when the worker is initialized. And that's it. When you create a new worker, these are the only 2 elements they will contain. So what does a worker's cute message handler look like on a block diagram? What you see here is the block diagram of a worker's main VI, so it's cute message handler. A worker's queued message handler is designed to have the same look, the same feel, and the same style as the LabVIEW queued message handler template, and contains only the most fundamental parts of a queued message handler, keeping the design simple and easy to understand. At the top here, we have an event handling loop, which is optional. Below that, we have a message handling loop, which every worker is required to have. At the beginning of the message handling loop, we have a VI, which dequeues messages from the worker's message queue. Message data is then acted upon in the case structure, whose case is selected by a string. And finally, we have an error handler. And the blue wire that you see that runs throughout the block diagram is a cluster of data where you can add your own data to be acted upon in the loops. A worker requires these 4 cases for its proper functioning in the framework. The first 2 cases are required for the initialization of the worker, and the last 2 cases are required for the shutting down process of the worker. And so these are the fundamental parts of a worker, and a worker's application would simply be built out of several queued message handlers that look like this. So how do you build the frame of a multi-process application using workers? A common interface connects workers together, allowing you to plug a worker directly into another worker so that you can quickly build up the frame of a multi-process application. This makes both creating and scaling the frame of a worker's application very quick and easy. And through the use of scripting tools, this is an automated process. So the first way to connect workers together is by statically linking them using the create add worker scripting tool. Using the create add worker tool that you see here on the left, you can create a new worker and plug it into a pre-existing worker as a statically linked sub-worker. And when used together with the worker hierarchy viewer tool, shown here on the right, you can watch your application's call chain hierarchy grow every time you add a new worker to your application with the create add worker tool. So let's take an example. Let's say I wanted to build the frame of the continuous measurement and logging sample project, which consists of 3 queued message handlers, one for the user interface, one for the acquisition of data, and one for the logging of data. Using workers, I would first create a blank project, and then I'd use the create add worker tool here to create the user interface worker, which is the head worker of the application. And then I would use the create add worker tool twice more to create the acquisition and logging workers, plug them into the UI worker as statically linked sub-workers until we are left with the call chain diagram that you see here in the middle of the screen, which represents the frame of your application. I will demonstrate the use of these tools later on in the live demonstration. So what does the frame of an application that the tool creates for us look like in code? What you see here is the main VI of the UI workers. Is the main VI of the UI worker. So it's queued message handler. Here you can see the queued message handler of the UI worker, and below it you can see the main VIs of the acquisition and logging workers that were created and added to the UI worker with the scripting tool. And what you see here is a fully functional application. If I run the UI worker's main VI, each of the 3 queued message handlers will be launched sequentially. And if I shut down the UI worker's main VI, each of the 3 queued message handlers will be shut down sequentially. So as a developer, all I have to do now is to create the user interface code, the data logging code, and the data acquisition code. I don't have to develop the frame of my application myself. This task is performed for me by the framework and by the scripting tool. So in summary, by using the create add worker tool, anyone can create the frame of a multi-process application in LabVIEW with very little effort. The second way to plug a worker into another worker is by loading it dynamically on demand using the framework's API. The dynamically load worker VI, which is available on the worker's palette, you can plug workers into your running applications dynamically during runtime. To use this VI, as shown in the example down here, you simply wire to the dynamically load worker VI the object constant of the worker that you want to load, as well as any initialization data that the worker requires when it is loaded. This VI will then perform the following tasks for you. It will launch the selected worker. It will create a message queue for it. It will register the worker as a sub-worker with the worker it is called from. It will initialize the worker and pass it any initialization data that you have set. It will integrate the worker into the worker's debugger, and I'll talk about this later on in the presentation. And when the application shuts down, the dynamically loaded worker will also be shut down as part of the application's shutdown routine. So once you load a worker this way, there is nothing else you need to do in terms of application integration. So in summary, number one, you can use the create worker scripting tool, or number two, the dynamically load worker VI to plug workers together to create the frame of a worker's application. How do you send messages between workers? Okay, the framework uses a priority queue to send messages between worker message handling loop cases, and messages are enqueued into the priority queues through use of the framework's messaging API. Firstly, the framework uses the same queue used by the active framework. So the performance and features of the queue are the same as that of the active framework. By using a priority queue, developers can assign priorities to their messages so that they can decide which messages should be processed ahead of other less important messages. The framework allows developers to assign one of three priorities to their messages, either low, normal, or high. And there is a fourth priority, which is the critical priority, reserved by use of the framework for the initialization and shutdown routines of a worker's application. And unlike standard LabVIEW FIFO queues and events, the priority queue always guarantees that messages are dequeued in the same order they are enqueued for any given priority. So there are two types of messages that you can send within the framework. And the first type is a standard asynchronous message that can be sent to any message handling loop case of any worker. To send a standard message, you need to use the enqueue standard message VI, which is available on the worker's palette. So to send a standard message, two steps are required. First, you send the message, and secondly, you receive the message. So step one, you send a message to the case of a worker that expects to receive a standard message. To do this, you need to wire to the enqueue standard message VI, as shown below, the queue of the worker you want to send a message to, the case of that worker that will receive the message defined as a string. Optionally, you can send data along with the message, which can be any data type you like, since it is packed as a variant. And you can set the priority of the message, so either low, normal, or high. So that's step one. Step two is then the receiving of the message, in the case that you send the message to. And in this case, if you send data with the message, you need to simply convert it to the correct data type. And that's it. So you can send a standard message to any case of any worker, so long as you provide the enqueue standard message VI with the recipient worker's queue and case. Second type of message that you can send in the framework is a callback message. A callback message allows you to send a message from one worker to another and then receive a payload back from the second worker, where the message flow looks similar to that shown in the diagram here. To send a callback message, you need to use the enqueue callback message VI, and there are two versions of it. There's an asynchronous and there is a synchronous version. In this example, I'll present the synchronous version. So sending a standard callback message is pretty much like sending two standard messages. So there's 4 steps. First, you send the standard message, then you receive it, then you send a reply message, and then you receive it. So step 1, send the callback message to the case of another worker that expects to receive a callback message. To do this, you need to wire to the enqueue callback message VI. Again, the queue of the worker that you want to send a message to, and the case of that worker that will receive the message, again defined as a string. Optionally, you can send a payload along with the message. You can set the priority of the message. And for this VI, you can also set a timeout, since this VI will wait, since it's a synchronous function, until it receives a reply message back from the worker that it sends the callback message to. So that's step 1. Step 2 and 3 then occur in the case of the worker that you send the callback message to. And in this case, you simply need to use the callback easy reply VI, which will send a reply message back to the worker that it received the callback message from. And the input to this VI is simply a variant, so any data type that you like. Step 4 is then the receiving of the reply message, which occurs again in this case, where the NQ callback message VI will receive the reply data, put it as a variant, and then you can convert the data to the correct data type. So that's a brief overview of how to send both standard messages and callback messages between workers using the framework's messaging API. How do you debug a workers application? You do this by using the workers debugger, which is a dedicated debugger that has been designed along with the framework and is designed to make a workers application more transparent and more accessible during runtime. What you see here is the window of the workers debugger showing the debugger's task manager tab. The debugger's task manager shows you a tree list of all the workers that are running in a workers application, along with the worker's clone ID, since every worker's main VI is a shared clone, as well as the status of a worker. A worker can have a number of different statuses that are assigned to it by the framework to provide you with feedback during the initialization and shutdown routines of a worker's application. There is also a right-click menu for the Task Manager tab. The option I want to mention here is the option called Open Running VI. This option allows you to jump into the running clone of a particular worker. So for example, if we right-clicked on this highlighted row here, on the logging worker, right-click and select Open Running VI, we will jump directly into the running instance of the logging worker, where you can then debug it with the standard LabVIEW debugging tool. So highlight execution, adding breakpoints, etc. So in summary, the debugger's task manager shows you what's running and allows you to jump directly into your running queued message handlers. The next tab of the workers debugger is the message log tab, and its purpose is to show you the flow of messages at runtime throughout your multi-process application. The message log shows you a timestamp list of all the messages that have been sent in an application, showing you where a message was sent from. So in other words, which case of which worker enqueued the message, to which case of which worker dequeued the message. So you can see enqueue to dequeue points of a message. It also shows you when and where any errors have occurred in your application, and it also allows you to apply string filtering on any of the columns so that you can, for example, see messages only sent from a particular worker to another worker. There is also a right-click menu for the message log tab. The option I want to mention here is the option called Go to Case. This option allows you to jump directly to the case of a worker where an error has occurred. So in this example here, this highlighted row, if we selected this row and then right-clicked on error 91 and selected Go to Case, we would jump directly to worker A's get counter value case, which is the case of the worker where the error has occurred, so that we don't have to manually search for the error through the Project Explorer and through Edit Our Code, saving us time when we are debugging our code. So in summary, the message log makes your running code more transparent by showing you the flow of messages and errors in your application at runtime, and the right-click menu allows you to jump directly to parts of your code where errors have occurred. So that's an overview of the workers debugger, and it really plays a very important part in developing applications efficiently with the framework. While a workers queue message handler has the same look and the same style as the LabVIEW Key Message Handler template. Because a worker is a class, the class provides modularity with inheritance. Now, I need to stress this again, but as mentioned before, developers can comfortably develop with the framework without any object-oriented LabVIEW experience, since the framework was developed for those at the core 3 level and above. And you only need to understand that a worker is much like a library with its own data type. But for those of you that do have object-oriented LabVIEW experience, you can use inheritance to your advantage to develop applications with the framework, and I'll explain this now. So by default, every worker inherits from worker.lv class, which is the parent class of all workers, and this is where the framework's common API exists. Now, say you wanted to add your own common code and features to every worker. Instead of adding duplicated code into every worker, you can inherit your workers from a custom base class. And in this base class, you can put your common code, such as common VIs, common data, even common message handling loop cases. It can be used by every worker that inherits from it, reducing the need to add this code into every worker and resulting in overall less code in your projects. You can also use inheritance to override the framework's public API. For example, you could override the error handler, the framework's error handler that exists on the block diagram of every worker, so that you can add your own custom and common error handling to your applications. You can also use inheritance to create hardware abstraction layers, whereby your hardware abstraction layer's common interface will exist in an abstract base class, and your specific implementations will exist in every worker that inherits from that class. So in summary, these are just some of the ways that you can use inheritance to help you develop applications with the framework. And it really is up to every developer and what level of LabVIEW experience they have, whether or not they choose to develop with the object-oriented possibilities of the framework. That's the main overview of the main features of the framework. Quickly now, I want to present the main new feature in the latest version of Workers, which is Workers 3.1, which came out last August, I think. And the main new feature in Workers 3.1 is the Workers library, which over time will evolve into a library of pre-built workers that can be easily integrated into your applications. So this is what the current window of the Workers library looks like. In the next version of Workers, it looks fancier than this. But for now, we have this, and we have one worker in it, containing a message pump. So the message pump is a worker that comes with the framework. And by using the Workers library tool, you can add a copy of this pre-built worker into your projects, which you can then use in your applications. In the future, I plan to add more workers to the library, and I also plan to add third-party support to the library so that other developers can contribute their own pre-built workers to the library to be used by others in the community. So now we get to the live demonstration part of the presentation. In this live demonstration, I'm going to start from a blank project, and then I'm going to use the scripting tool to create the frame of a small Workers application. And then I'm going to add a message pump from the Workers library into the application to show you how everything integrates together. I will now switch to LabVIEW. So I'm using LabVIEW 2018 for this demonstration. So I'm going to first create so once you install LabVIEW into Workers through the VI Package Manager, you can create a blank project. You need to save the project before any location will do. Okay. So you just need to save the project before you add any workers to it. And then I'm going to go to Tools and go to Workers Tools, which opens up the Workers Tools menu. So here we have the Created Worker tool, which I explained. This opens up the Workers Debugger. Here we have the Hierarchy Viewer tool that I also went through quickly. And here we have the Workers library, so the 4 tools. And actually, quick note, I'm using Workers version 3.1.1, which will come out this week. The only difference between 3.1 and 3.1.1 is that there's a patch for LabVIEW 2021 Service Pack 1. In that version of LabVIEW, some of the icons are not displayed correctly that the tools create. So that's the only difference between 3.1 and 3.1.1. It only affects LabVIEW 2021 Service Pack 1. So I'm going to select Create Add Worker. So for this example, let's create the frame of the continuous measurement and logging sample project that I already have been through, just to make it familiar. So the first worker we want to create for this application will be the user interface worker, so the user interface queued message handler. So at the top here, we have the option to select the type of worker. We can select a worker from with an event handling loop, or without, or from a template. We want to create a worker with an event handling loop. For the user interface, we can give our worker a name in this field here. So select UI. We don't have to worry about inheritance because we're not using that feature. We can give the icon a header, user interface, and then we select OK. The tool will now create a new worker, add it to the project, and for the very first worker that you add to a project, this pop-up will come up. It says, to run your new worker, you need to use a launcher VI. Would you like to create one for your new worker? Select OK. You always need a launcher VI to launch the head worker of an application. So now in our project, we can see that we have a launcher VI and we have one worker. If we have a look at the contents of the worker, we can see that it contains a main VI, which is the queued message handler, and then an initialization data cluster. If I open up the main VI and have a look at it, we can see that it's just a standard queued message handler containing the 4 default cases. Of course, we can add more cases to our event handling, to our case structures. And I'll show you how to do that in a minute. So I'm going to open up the worker hierarchy viewer tool. This little icon, this little button at the bottom of the tool will open it for us. There we are. And now if we select the UI worker and say view tree, we can see that our application only contains one worker. So now I'm going to use the tool to add the logging and acquisition workers to the UI worker. So let's create the acquisition worker. Acquisition, and we can give our icon a header. And at the bottom of the tool, we have the option to add our acquisition worker to the UI worker. So select UI. Okay. The tool will create a new worker and integrate it into the UI worker. So now we can see the acquisition worker in the project. And if we update the hierarchy viewer tool, we can see now that the acquisition worker has been added to the UI worker. So I'm going to perform this task again one more. The logging worker, again, add this to the UI worker. Select OK. And we have three workers in our project now. And if we refresh the tree, we can see that our worker call chain looks like this here. And if we have a look at what the main VI of the UI worker looks like, we should see that below the queued message handler of the user interface worker, we have these are the main VIs, so the queued message handlers of the acquisition and logging worker, respectively. So what we've created here in just a few minutes is the frame of the continuous measurement and logging sample project using modular and scalable LabVIEW queued message handler template style queued message handlers. And as I said before, this is a fully functional application. If I run the application, I'll open up the workers debugger first so that you can see the application run. But if I run the launcher VI, we can see now that our application is running. And we have our UI worker, our acquisition worker, and logging workers, and all those workers have been initialized. And if we go to the message log, we can see that some messages that have been sent back and forth during the initialization of the application. If I stop the application, you can see now that the status of the workers have changed to aborted. So what I'm going to do now is I'm going to add a message pump to the application from the workers library. So normally, let's add it to the acquisition worker. Theoretically, we would have, or practically we would have in the acquisition worker, we would have code that acquires data from a piece of hardware, so a compact reader or something. So we would want to probably poll the hardware for data at a fixed period. And we can add this polling functionality through the use of a message pump. So I'm going to go to the workers tools, go to the workers library. I'm going to select the workers library and say add selected worker to project. And it's going to add a copy of the message pump into the project, and then we can use that worker in our application. So this is the message pump. The message pump, it's just a worker, but there's a few wrappers around some of the NQ message VIs to create a public API for the message pump worker. So I'm going to open up the block diagram of the acquisition worker. And I'm going to add a case to this worker. I'm going to add a case to this worker. So say add case after. I'm going to call the case read data. And here in this case, we can put some code that can read data from a piece of hardware. But we want to call this case, say 10 times per second. So after the worker has been initialized, I want it to load a message pump. So from the message pump's public API, I'm going to drag and drop the create start VI from the message pump, wire it up. And the inputs to this VI, number one, are I can create a case. I can select the case that I want to send a message to. So in this case, I'm going to send it to read data. And I'm going to define a period at which this message pump will send a message to the read data case. So 100 milliseconds. And I need to create a pump name. Okay, so what's going to happen now is when the acquisition worker loads, it's going to dynamically load a message pump. That's what this VI does. Behind the code here, I can show you quickly. Here we're using the dynamically load worker VI, and we've attached to it the object constant of the message pump. So it will, at runtime, dynamically load an instance of the message pump worker. And then the message pump will, it's an event-driven timer. It will send a message to the read data case at 10 times per second. Yeah, so I can put an indicator actually. Yeah, let's create an indicator here so that we can actually see what's happening on the block diagram. So when I run the application and jump into the running instance of the acquisition worker, I should see this number increment at 10 times per second. So let's see if all this works now. Again, I'm going to run the launcher VI. We can see now that our message pump is in our application. If I right click on the acquisition worker, let's say open running VI, we can see now that our numeric indicator is updating at a rate of 10 times per second, which means that this case, the read data case, is being called 10 times per second. So that's pretty much how you build applications with workers. It's very modular, very scalable, and is quite easy to use. So back to the presentation. So in summary, Workers has been designed to help developers at the Core 3 level and above to easily create modular multi-process applications in the style of the LabVIEW queue message handler template. The framework allows you to easily plug workers together to build up the frame of a multi-process application. And the priority queue allows you to select which messages should be processed first ahead of other less important messages. The workers debugger shows you what's happening in your applications at runtime and allows you to jump directly into your running queue message handlers. The workers library will evolve into a library of pre-built workers that can be easily integrated into your applications. And because workers is an object-oriented based framework, it allows you to develop your applications using inheritance, resulting in a cleaner architecture and less duplicated code. To help you get up and running with workers, there are 3 sample projects and an official user guide. And there are also a few tutorial videos that I've created, which are available on the Workers YouTube channel. And Workers is available through both the NI Tools Network and through the VI Package Manager. So to end, Workers is a Qt message handler based framework for LabVIEW. It is easy to use and learn by anyone at the Core 3 level and above. It allows you to develop applications in the style of the LabVIEW Qt message handler template while supporting an object-oriented architecture at the same time. And you can use Workers to develop applications ranging from a single Qt message handler to applications consisting of hundreds of Qt message handlers. And I really hope that this framework will provide a way for developers, and especially developers with a lower level of LabVIEW experience, to develop multi-process applications in a simpler and more efficient way. And that's the end of my presentation. Thank you for listening.
Thank you, Peter. It is really great, amazing work. And
Thank
you
you
for presenting this in our group as well.
Not a problem.
Okay. Yeah, I think we have 2 questions from the participants. From Karthik, is the first question is, how are the files organized in the disk for a worker module?
For a worker, well, I can show you actually what we created. So if I go to the project and have a look at the files, so we created our project under new folder 2, and 2 folders were created. One for launchers. There's only 1 launcher. And each worker was added to its own folder, and the data within the class itself, then it's just flat. So all the VIs within a particular worker, it's just flat, but each worker has its own subfolder.
Okay. Any reason for keeping it flat under workers? So maybe like subgrouping?
Well, you could subgroup. Yeah, then I would. But okay, so if I subgrouped, for example, if I go into the UI worker, then I could have a folder for setup, for type defs, for worker initialization. That is possible. It's not set up like that by default. I guess you could have, yeah. What I've seen is that most folder structures within a class itself is pretty flat, but the classes, of course, are in separate folders, because they're pretty much libraries with their own data type.
Yeah, I think even DQMS is in the same way. So usually, my personal preference is to maintain the same hierarchy of whatever is in the project to be in the disk as well, so that when we browse, it will be easy to select something instead of having everything flat. So that is fine. Maybe if that way to make it subfolder, or maybe give it as an option to the user, that will be very useful.
Okay, yeah. Yeah, at the moment it's just flat. I would have to create a tool that would kind of iterate through all the virtual folders and then create. Okay, I'll think about that. Okay.
Sure, Peter. Yeah.
Thank you.
A lot.
Yeah.
Great. So the second question is also from Karthik.
Yes, the license.
Yeah, great.
So there's no specific license. I am not an expert about licenses. I've had a look at the different types, and they still confuse me. I mean, the framework is free to use for commercial use and for non-commercial use. So you can pretty much do what you like with it.
Sure. Yeah, I think when we actually want to use it in a commercial application with for a customer, right? Usually we need the specific license. So my general recommendation would be to either go for BSD or MIT, which is like,
okay.
Those are the 2 most common commercial friendly licenses.
Okay.
Whereas GPL and LGPL are not so commercial friendly, where you have to also release the source code of whatever you're building on top of it.
Oh, that's interesting. Okay.
So GPL
Yeah.
and LGPL is something that if you wanted to make it commercial friendly, it's not recommended to go with GPL and LGPL. Whereas
Okay.
PhD and
Friendly.
MIT, I think there is only like a 3 clauses for both of them. It's just a very short paragraph.
Okay.
So I would probably recommend one of them in case if you're open for project.
I see. Okay. BSD or MIT, correct?
Yes. Yeah.
Yeah,
BSD 3
okay.
clause or MIT. Yeah.
Yeah. I looked in. I posted a question on LinkedIn about a month ago, I think, actually asking other developers what they recommended, and there's a few answers. And I think BSD came up a lot. MIT as well, actually. Do you know anything about the Apache license?
Yeah, Apache is also commercial friendly. Apache 2.0,
Because
MIT, BSD, all these are commercial friendly licenses.
yeah, okay, Apache 2.0. Because I think, for example, some of the NI tools for active framework uses Apache license, I believe.
Okay.
Yeah. Or 2.0. Okay. Thank you. Any other questions?
Yeah, we have one more questions from Prashant
Yes.
Singh. So
Okay.
for which kind of application worker are more friendly than other coding styles?
So I use workers for any application that requires multiple processes to be running in parallel at the same time. And again, the continuous measurement and logging sample project that comes with LabVIEW is a good example of that, because you have 3 independent processes that are communicating. They're running asynchronously, and they're communicating via the queues. And of course, you can scale that. I mean, I've created processes we have a lot of different hardware, and you have a different worker acquiring data from each different piece of hardware. And then you'll have a few workers which are logging data. You have a few different kind of user interfaces embedded in subpanels, and you often want to modularize all those processes and the user interfaces as well. So I'll create a worker for every data acquisition process and for each subpanel, and then I'll also have workers which will connect the processes together to kind of transfer the data from, say, a certain piece of hardware to one of the user interfaces, one of the subpanels.